Good morning. Welcome to July 26 LeetCode Challenge. Convert sorted array into binary search tree. Given an integer array nums, where the elements of the are sorted in ascending order, convert into a height balanced binary search tree. A height balanced binary search tree is a tree in which the depth of the two subtrees of every node differ by more than one. So we have basically a sorted array here, right, of such a sorted array given there, and we want to convert that to a height balanced binary search tree, which looks like this. So basically, you would have not this actually. You would convert the array looking above to something that looks like this at the bottom. All right. So basically, you have it's not too different. It's just balanced. Likewise, we're given an array nums of 1 to 3, and then we could have an output of 3 to 1 as well. So both are height balanced binary search trees. Here constraints here we have length of nums between 1 to 10 to the 4th, index between negative 10 to the 4th to 10 to the 4th, and nums is sorted strictly in increasing order. So that's good. That's good to know. So a couple of things we should note about the height balanced binary search tree. One being all elements of the left subtree are less than root value, right? All the elements on the left subtree are less than the root value. All the elements on the right subtree are greater than the root value. All the left subtree element is a height-based subtree, so it's so if the entire tree is a height balanced binary search tree, then the nodes themselves are of the left side subtree is a height balanced binary search tree as well as the right. The difference between the height of the left subtree and the height of the right subtree is at most 1. At most more than 1. Never differs more than 1. So that's something to note. So let's say if we let left side equal to 0 and right side equals n minus 1, we could choose a midway point of the array of elements of the indices from left to right as root value, and then we perform a depth first search on the left subtree as root.left, and then we do the same thing on the right subtree, root.left and root.right, and we do a kind of like a depth first search algorithm to find the midpoint in between. Yeah, let's go about doing that. So instead of writing a depth first search definition within it, I'm just going to use sort binary search tree as the depth first search algorithm. So let's see how we do that. So if not array list nums, then what we're going to do is return none, because that does not exist. So next thing we want to do is find mid element here. So we call it mid, I guess, and we're going to do the length of nums divided by 2. Next thing we want to do is create a node. So we have a tree node class, class tree node here. We're going to make one of those. So we're going to put in, call it root, and we're going to assign that to be tree node, and we're just going to take in the nums at index mid. Because we want to essentially build we're making our node here, and then we're going to put that pass through the mid value as our root. Next, we're going to basically start adding nodes to our root binary search tree. So first of all, we're going to add the left side. So what we're just going to do is assign root.left to be a recursive call on the binary search tree. So sorted array to BST. I'm just going to copy that actually, just to make sure. Can't trust my my typing skills. And what we do is take nums at index. So we want everything from to the right of nums, of the midpoint. So I'm going to do this. Take the slice of from the mid to all the way to the right. And then we're going to do the same thing to the right this time, but this time we're going to take the slice to the left. So right.self.sorted array to binary search tree, take nums at the midpoint plus 1 all the way to the n. So all the elements on the left. And at the end of this, we want to return our root. So this right here is a classic depth first search algorithm, and it's going to create, hopefully, a height balanced binary search tree. I hope so. Finish. That looks good. Alright, accepted. Awesome. So this question is rated as easy, which seems to be the case. Time complexity is big O of n, for n representing each number, each element in our array, which we need to make a node for. Space complexity is without counting the output itself as a space. So we have the entire algorithm, depth first search algorithm, is big O of log n, but I think you need to take the height into it as well. So the height of the binary search tree itself. But yeah, that's it. Have a great day.